When it comes to conic sections in polar coordinates, we're going to be looking at this very surface level. We'll be looking at the eccentricity and how that determines the shape of the conic section that we're working with. See this form or this form, or manipulate your equation into this form, one of these, then we can pluck out the E and identify if we have an ellipse, a parabola, or a hyperbola. If the eccentricity E is between 0 and 1, we have an ellipse. If it's equal to 1, it's a parabola. If it's greater than 1, we have a hyperbola. Let's look at an example because then it'll make the most sense. Looking here at this first one, R equals 6 over the quantity 3 plus 2 sine theta. I'm going to manipulate this so that there is a 1 for the first term in the denominator. In other words, let's divide everything by 3. I can see that the E is equal to 2/3. Okay? Now, the top is EP. So I could use that fact and say if EP is equal to 2 and we know E, this is solvable. Okay. All right. A couple things we're going to get from this. Since E is 2/3, we're going to come up here, and this tells us that this is an ellipse. Okay. And we don't often think of ellipse having a directrix, but they do discuss that. From this, once you know the p-value, we have a directrix at y equals, it's positive or a negative p. It won't be both. I'll show you which one it is here. Basically, our equation has a plus sign in the denominator, so that's on top. So we'll be working with the one that's on top. So that means y equals 3 is a directrix. This is the equation that we just graphed. So what they're saying is one of the focal points is at the origin. Okay, look at this next one. R equals 12 over 4 plus 5 cosine theta. That format, we'll divide everything by 4. Matches this one. Numerator divided by 4. So we are going to manipulate it so that there's a 1 first in the denominator. And if we do that, we can see that our eccentricity is equal to 5/4. It's greater than 1. We know we're working with a hyperbola. So I know that this shape is a hyperbola. Okay. Let's find the p-value. EP, the numerator, is equal to 3. I know E. Don't know P, but we can solve for it. P will equal 12/5. Okay. Now, looking at the forms that I have, the one that has the cosine is the top one. The equation that we're working with has a plus in the denominator, so that's the top. So that's the top. So X equals P, which is 12/5, is the directrix for here. We're not used to looking at directrix when it comes to hyperbolas, so I'm going to keep moving on and not focus too much on that. We identified the shape. It's a hyperbola, and we identified the p-value. All right, one last one. We're going to do the same thing here. We're going to make it so that the first term in the denominator is 1. So here I'll divide everything by 2. 7/2 on top. 1 minus 1 sine theta. Our eccentricity is a 1. Okay, I'm going to go up to our form. When eccentricity is a 1, we're looking at a parabola. Okay. It's a minus sign. So we're looking at the bottom operation. So the bottom symbol here and our directrix here will be y equals, what was the p-value? Well, if EP is equal to 7/2, and we know E is a 1, P is 7/2. But since it's a minus sign, we're going after the symbol on the bottom. So our directrix is y equals -7/2 or -3.5. We are used to seeing the directrix for this parabola is y equals -3.5. Here's our P, here's our E, and we know this is a parabola. And let's look at the graph of these, all three of these. All right, here's the graph of the first one. Here's the hyperbola, the second equation that we graphed. And here's the parabola, the last one that we graphed. This is the one we're used to seeing a directrix on. So the focus is at 0, 0, remember? Looks like our vertex is at -1.75. That distance, again, will give us a directrix at y equals 3.5. So that tracks with what we have learned about parabolas.